On to conservation of energy. Energy is a conserved quantity. So here, I've got to warn you, some of what you have learned is not going to be correct. For instance, if a quantity is conserved, that means the quantity cannot be created or destroyed. Wrong. That is very dangerous to say. In physics, the phrase cannot be created or destroyed really only works for mass. Conserved really means the total before equals the total afterward. So let's see how that works. Energy is a conserved quantity. That means two things. Either the total energy before something happens is equal to the total energy after something happens, or there is more energy after than before because energy came from somewhere, or there's less energy after because energy went somewhere. So let's go back and read that either or very closely because it is a little wordy and it's important to have this nailed down. So energy is a conserved quantity. That means one of two things. Either the total energy before something happens equals the total energy after something happens, or there's more energy after than before because energy came from somewhere, or there's less energy after than before because it went somewhere. So you may have energy coming into a system, which would lead to more energy than before, or you may be losing energy to the system in terms of thermal energy, perhaps, from friction. If the total energy of a system before equals the total energy after, then the system is called a closed system. Please add this to your vocabulary. Understand completely what a closed system is. Total energy before equals the total energy after. As you're writing to answer some justifications for questions as the year goes on, you have to reference whether or not this is a closed system or not. If the total energy before is not equal to the total energy after, then the system is open. That means the energy was received from surroundings or given off to the surroundings. Here's a simple example. A cart is released from rest at the top of a ramp that is 1.8 meters off the ground. How fast does the cart move upon reaching the bottom of the ramp? Initially, the cart has no velocity but does have a height, so the cart has gravitational potential energy. Finally, the cart has velocity but does not have height, so the cart will have only kinetic energy. So at the beginning, no velocity, but there is height, so there's potential energy, and at the end, when it comes down here, the cart has velocity but does not have height, so it has kinetic energy. Since we start with gravitational potential energy and kinetic energy, we can set up the equation. We know the gravitational potential energy in the beginning has to equal the kinetic energy in the end, because we're assuming it's a closed system in this instance. And with a closed system, the amount before equals the amount after. If we solve for the final speed, then we see m on each side, they'll cancel, and we're left with g times y equals 1/2 v squared. V squared equals 2gy. Multiply 2 on each side to get rid of the fraction, so we are left with 2gy, and we have 2 times 10 times 1.8, and then we take the square root of that to get 6. Take the square root because this is squared. Another example. If we give the cart a quick push at the bottom of the ramp, what minimum speed must the cart have to reach the top of a 1.8 meter tall ramp? Initially, the cart has velocity but no height, so the cart only has kinetic energy. Finally, when the cart gets to the top, the cart will have height, but it'll stop at the top because remember, we're just giving it a push just to get it to the top. So it ends with gravitational potential energy. Because we start with kinetic energy and we end with gravitational potential energy, we can set up the equation. Kinetic energy in the beginning equals the gravitational potential energy in the end. It is exactly the same as before. That means if the cart is released from rest at the top of the ramp and attains a speed v at the bottom, the cart must have the same speed v at the bottom to take it to the top of the ramp. Make sense? Goes down and ends up with some speed, then that same speed going back up should get it to the exact same location at the top. If this cart has an initial speed less than 6 meters per second, the cart would stop and turn around before reaching the top of the ramp. If it has a speed greater than 6 meters per second, it's going to get to the top and still fly off. If we have friction, then friction's entire job is to take kinetic energy away and turn it into thermal energy. Don't forget, friction is the name of the force, not the name of an energy. Friction is like the IRS of energy. Just as the IRS takes your money in the form of taxes, friction takes away a system's energy. The money doesn't cease to exist, it just becomes useless because the government has it. Likewise, energy lost to friction cannot be used to do anything more. If we have a 10 kilogram block released from rest at the top of a ramp, that is 1.8 meters off the ground, the block reaches the bottom of the ramp with a speed of 4 meters per second. How much energy is lost to friction? Initially, the block has no velocity, but it does have a height, so the block has gravitational potential energy. Right? Finally, the block has velocity, but does not have height, so the cart has kinetic energy. Typo there. So the block has kinetic energy. Also, some energy was taken away by friction, so at the end there is some thermal energy in our system also. Start with gravitational potential energy, end with kinetic energy and thermal energy. Right? So we start with gravitational, and then we end up with some kinetic and some thermal energy. And there is still an equal sign. These two added together will give us this. Our speed isn't going to be the same because we have something else stealing from us. We cannot cancel m because it has to appear in every term to cancel. Mass is not in the ethermal term. So let's just plug in numbers. We started with mass of 10. G, we're going to use 10 for easy calculations, and then the height was 1.8 equals 1/2 of 10 times 4 squared. Plus our E thermal. We can see we end up with 100 joules of E thermal energy. That's a lot of the energy that was stolen. And that'll do it for this one.